Okay, so this lecture is on what I'm calling computational creativity. And this is more or less an introduction to generative AI. And so if you're at RPI and you're taking my class next semester, this is kind of like the one lecture preview of all the stuff we're going to talk about in that class. And so the reason that I have this sheep as the kind of mascot for this class is that last year, my wife came back from Honest Weight Food Co-op, which is this place in Albany that has great food, but the prices are a little bit high. And this thing of sheep cheese that she bought, I saw in the refrigerator with the price turned toward me, it was $23. I was like, how could this one container of cheese be $23? And so that prompted me to ask DALL-E to render me a picture of the sheep that was making all of this money off of this high-priced sheep cheese, right? So this is the sheep living large in the field, right? And so this was one of the very first DALL-E 2, or one of the first DALL-E instantiations. So things have gotten a lot better since this photograph was rendered. And to give you some sense of how quickly the field has come, so only 10 years ago, in terms of generating realistic human faces, for example, this was kind of where we were at in 2014. Recognizable human faces, but they look kind of at the level of some sort of grainy passport or newspaper photo, right? And even 2015, 2016, things looked a little bit rocky. Then there were some real innovations, 2017, 2018. So suddenly by 2018, 2019, you could make human faces that looked extremely photorealistic. And one of the reasons for that, as we'll talk about, is that there were lots and lots of databases of faces that allowed these machine learning algorithms to be trained. And so that kind of progress continued, and then it was kind of more like a couple of years ago when when DALL-E first came out, that you suddenly began to be able to make things other than these faces and cars and things that were in these computer vision databases. Suddenly it became possible to ask for a picture of a kangaroo or a picture of a sloth wearing a knitted hat, right? Things that had never been actually simultaneously pictured in the same data set. Suddenly you could make these photorealistic versions of these. And of course, as you know, you can also make things in all sorts of different styles and so on. So, and this was just last year, so I have to update my picture now to be more like what we can do in 2024 going into 2025. Of course, on the text side, we have the rise of ChatGPT and other sorts of generative text algorithms, right? So keeping with the sheep theme, I asked ChatGPT, this is an early version, to tell me a story about, this gritty crime-fighting sheep. And of course, it produces something that would be great, if I have a kid to tell them a bedtime story about the crime-fighting sheep. It's grammatical, it makes sense, it's fundamentally, very credible, right? But at the time, then I asked it, okay, tell me about Rich Radke, unprompted. And it says, okay, I don't have any information about Rich Radke. Tell me something about. I said, oh, he's from RPI. And then ChatGPT was perfectly willing to tell me all about Rich Radke, including not just professor of ECSE at RPI, but also, a graduate. So, not only did I join the faculty in 1998, this other guy was a graduate in 1998. He founded Infinity Games, a mobile gaming company, Forbes 30 under 30, sounds like a great guy. And then this other Rich Radke was a guy on the RPI Board of Trustees. I was like, oh, that's pretty interesting. I've never heard about these other Rich Radkes, so tell me more about them. Happy to give me all sorts of information about these other Rich Radkes. And I said, well, actually, I don't think either of those people actually exist. Says, oh, I'm sorry, actually, there is no such guy named Rich Radke. So, one thing that I had heard ChatGPT described as is mansplaining as a service, right? Basically, it will give you some sort of authoritative commentary about anything that you ask it about. And it'll be perfectly confident until you challenge it, say, oh, actually, well, no, I made it all up, right? So certainly now with the modern versions of GPT, like 4.0 and so on, it's not just necessarily next token prediction or next word prediction anymore. Now it's integrated with Google searches or with calculators, and so it's a lot harder to tell exactly what's going on under the hood when you ask these algorithms something. And so as machine learning engineers, I think it's important to be aware of what's called the hype cycle, right? So this is a famous kind of thing that's applied to all sorts of technology. So basically, generative AI is kind of here. It's on the upward slope of every company is talking about AI. Everything has to involve a large language model. This is going to be the thing that transforms our society, right? But I think it's important to be a little bit skeptical, right? So as a researcher, I'm more of a computer vision researcher out here on the kind of far end of the hype cycle, where after, a peak of people talking about all the things that we could do with computer vision, I think that we've kind of converged to a point where we understand what it can and can't do and what it's good at. Whereas here, generative AI is still kind of in the, everyone's throwing billions of dollars of investment and it's going to change the world, right? So I think it's kind of important to be aware of the hype. And every time I talk to an administrator in our department or someone else, I'm always cautious to say, like, the word AI, as we talked about in the very beginning of this class, doesn't really mean anything, right? It's kind of whatever anyone who wants to sell you AI technologies wants it to mean, right? So this is sci-fi author Ted Chiang, who basically says that the words AI, artificial intelligence, were created kind of like by a think tank group in the 1950s, and then the idea stuck because it sounds super cool, but it doesn't really mean anything. And if you were to talk about what we're really doing today in machine learning, it's really just kind of a form of applied statistics where you have a huge amount of trained data, massive GPU-enabled architectures to train on this trained data, but applied statistics doesn't sound as cool as artificial intelligence. So, and as you know, we talked a little bit about deep learning. Fundamentally, what's under the hood of all these, generative AI systems is fundamentally some massive neural network architecture that, you'll see these things in papers that have a zillion layers. Now you know what all these things mean, right? We've got convolutional layers, max pooling layers, dropouts, and then different dimensions, and there's like different levels of skip connections. It's kind of like, imagine that you've got like a mixing board that's got a zillion levers and knobs, and it's just a question about how do you use, at the end of the day, backpropagation to tune all these knobs to achieve the best performance on your training set, right? And honestly, to me, this kind of thing, at some point, I don't find it very interesting. Like, I find it deeply boring to talk about exactly what the architecture of these networks is, because honestly, to me, it's just a heuristic for what seems to work the best, right? So, what may work today, right now everyone's talking about transformers is the new hotness, right? And yes, it seems like transformers are great at solving every problem, but maybe 3 years from now, transformers will be passé and it will be some new thing, right? So, I think it's more important to kind of talk about what is the input, what is the output, what is the cost function, and I'm not really that bothered by what's actually under the hood of the technology. So, as you know, the underlying thing behind all these machine learning optimization algorithms is like gradient descent, right? So gradient descent is still the workhorse of optimization. And of course, you all know what this means, right? We have some sort of cost function. It may have maybe multiple local minima. You stand at you stand where you start the initialization, and you take a small step down the hill in what seems to be the direction of biggest decrease. And you keep on doing that, and hopefully you'll certainly find a local minimum, and if you're lucky, you'll find a global minimum, right? That's what stochastic gradient descent is like. And I should give credit, so there's this artist / computer scientist, Mia Tang, who makes these kind of cool machine learning graphics. And of course, we learned about backpropagation, right? Which is all about, you have a whole bunch of input-output examples, and you slowly push back the errors you made in classification or regression by adjusting the weights backwards as you go through the network, right? This is exactly what you did on exam 2, problem 5, right? Is kind of like pushing an error at the output back to refine the errors in the weights at the input, right? And again, no matter how complicated the neural network is, fundamentally backpropagation is the workhorse for solving the problem. Okay, so before I talk about modern generative AI, I just want to give you some flavor, because my course is really about, at the big picture, how are people using technology to create art or create, artifacts that could be seen as creative, right? And so just to give you some sense of the history of that, right? So this is one of the earliest, what I would call computer-generated art forms. This researcher, Ben Leposki, who took pictures of his oscilloscope and traced out these kind of cool spiral patterns, right? This was, again, before the digital computer, right? You could still kind of make these kind of cool swirly patterns, and these were printed out and hung up in museums, and they look kind of cool, right? There was also a whole kind of wave of what I would call procedurally generated or random generated art, right? So this is kind of basically like a contraption that you could get on like a bicycle, and each person who was riding this weird contraption would trace out some sort of different artwork, right? So there's definitely some randomness in this result, right? But there's also kind of like some sort of human-driven aspect to it, right? It wasn't fully automatic. There was a big wave of interest in the late 60s in terms of thinking about how could these new computers be used to generate, art, right? And so there were these symposia about how could this new device be used to mediate or help create art. And so early programmers, so this is actually a great example. So there's a woman named Lillian Schwartz who actually was the in-house artist at Bell Labs in the 70s, who learned how to use digital computers to make these kind of early procedural / random artworks. She actually only recently died, and so you can find her obituary, like in the New York Times, for example. It's interesting to read about her. Other researchers, like Vera Molnar and Grace Hertlein, learned Fortran and early programming languages in order to make these kinds of new art forms, right? Things that look kind of, super simple and quaint to us now, but at the time in the 70s were like super innovative and amazing, right? And then there were people who were, again, thinking about algorithms for making art. So who here has been to Mass MoCA? Come on. So this is a great thing to do over the Thanksgiving break, right? So Mass MoCA is a wonderful art museum in the Berkshires, about an hour east of here over the Massachusetts border. It's a very nice drive. Mass MoCA is housed in a former textile factory, so it's got these huge ceilings and massive galleries. Like one of the galleries is like the size of a football field enclosed by these huge windows. So it's a beautiful place to visit, just as a building, and they have all this cool modern art in it. And one wing that they have is devoted to an artist named Sol LeWitt. So Sol LeWitt was not the person who actually physically created the artworks there, but he left behind instructions for how the artworks were to be created. So for example, he might say, okay, make 10,000 little rolls of paper, and on this wall, kind of like randomly pull out, red, yellow, and white pieces of paper and curl them up, put them into these holes. And this wall, you can add red, yellow, white, and blue, right? So the artwork in this wing, they're like, beautiful, colored, swaths of things. But the point was that they are kind of procedurally or algorithmically generated. He left behind instructions for how they should be made, but didn't make them himself, which you could kind of think of as like an algorithm for making art. Also, a very famous artist named Harold Cohen made a series of combination hardware-software devices. One of them, kind of collectively known as Aaron, was the name of his device that would basically be like a big plotter on a piece of paper that you go to a museum and you'd see this thing creating this kind of random but clearly somehow authored piece of art at the same time, right? So I'm not exactly sure how to describe what the algorithms were inside. This is a combination of randomness and pre-programmed stuff, but there was no artist's hand. This isn't just copying something that someone did. This is something that's being created on the fly. And so again, this is someone who also died not that long ago, and the details in the New York Times obituary are kind of interesting about his work. So now let's flash forward to the beginnings of computer-generated art and what scientists and researchers were trying to do, right? So one of the earliest works was from 1990, Haberly. And so SIGGRAPH is the main computer graphics conference, and it still is, where you see all this super cool cutting edge stuff. And so this researcher was interested in, how do you take either a photograph, this is clearly a photograph, and then this is more like a series of 3D rendered solids, and then create versions of them that look like they had been painted or sketched, right? So for example, here, this photograph has been kind of painted over with these kinds of like rectangular brush strokes, right? And here, these 3D objects have been kind of hatched in with geometrical lines that kind of are meant to give the kind of shading that a real artist might use in making the sketch. And so that was followed by work, and actually this was my college roommate, Aaron Hertzman. So he's actually quite well known in the world of computer graphics, and more specifically what's called non-photorealistic rendering, right? So he developed an early algorithm for taking and he was also a dual major, art and computer science. So he was an artist and also a scientist, and so he understood how artists create art, but also how computer scientists write algorithms. And so one of his early algorithms was taking a photograph and then laying down, broad strokes of paint, long, thick paint strokes, followed by slightly thinner and shorter paint strokes, followed by even shorter and smaller paint strokes to make something that kind of approximated what a painted version of the photograph might look like, right? And by tweaking the parameters of this algorithm, for example, how wide or how skinny the brushstrokes could be, you could get versions of the painting that looked like, Van Gogh, like long impressionistic strokes or pointillist strokes. It was actually very compelling, right? Although it is important, and actually if you take a look at Aaron's blog, it's a lot of interesting stuff about the intersection between art and technology. And so it's certainly not true, especially if you've ever painted a picture, that you start out with a mental model of, okay, I'm going to paint this picture, and I'm going to do so in this procedural way. Real artists are discovering the painting as they go along the way and changing their minds and fixing mistakes and deciding to go in different directions, right? So it's definitely a different mental mechanism than just trying to duplicate what your eyes see in a photograph, right? But still, this was early work that inspired a lot of other researchers. For example, one of the directions of this work was to then take video and make it look like it had been painted, right? And so here you can see that, you got these kind of brush strokes that stick to the sleeves and the pool balls and so on. So you have to kind of think about how is the temporal coherence of these strokes going to be maintained. And of course, then you could go in a much more abstract direction and have like these kind of like little oblong, ellipsoids that stick to things, or little swirly things that are much more, abstract, but still give a sense of what's going on, right? And so this, is, again, kind of evocative of what an artist might try to do if they were trying to make a video sequence. Another one of Aaron's innovations was a key paper called Image Analogies. And the idea was that you would take a input image and an output image, right? So for example, here, these are both paintings. This is like the actual painting, and this is like kind of basically like a low-pass filtered, blurry version of the painting. Or you could put a photograph in here instead. And the idea was to say, just like when you took the SAT, right, or the GRE, that you've got, this painting is to this picture as this painting, or this thing is to this picture, right? So the idea was that you show it one example of what you want the result to look like, and then you give it another picture and you say, okay, make me a thing that looks like that, right? And so this photograph then becomes this thing that kind of looks like a painting. And the idea was that instead of having to actually specify in the previous work, how long and how thick the brush strokes are, there are no necessarily brush strokes here. It's more like the B prime is created by looking for, similarities between B and A, and then trying to take the A to A prime mapping and apply them to this, right? So you could make these versions of photographs that looked like they had been oil painted, for example. Or, the other cool thing you could do with it was if you took, instead of the input being a photograph, you took the input being kind of like what was called a paint by numbers scheme, right? Where this is an actual picture, and this is somebody painting over and saying, okay, blue is river, and black is grassland, and red is forest, and green is, I guess, more grassland or something. And then this is your input-output relationship. Now you put in this picture here, which kind of is like, okay, I want there to be a river that does a loop-to-loop around a forest and so on. And you can kind of create these new pictures that, again, are fairly photorealistic, but are not actually ever created by a real camera, right? Just kind of like reasoning by analogy. And then there were lots of image processing techniques that came around the same time that would take images, and if you took the image processing class, you know about how to do like edge detection. So you could find the edges, and then you could kind of like amplify the edges and stylize the colors. These probably remind you of things like Snapchat or Instagram filters that you can kind of use to stylize your profile picture, for example. So all that stuff kind of, again, came around in the kind of late 2000s. This was before deep learning, basically. Then deep learning came on the scene. And so we talked about ImageNet, right? So ImageNet and AlexNet were kind of the first time that deep learning was used to really effectively do image classification. And someone realized at Google that they had this state-of-the-art Google image classification algorithm called Inception, or it was InceptionNet, I guess. And what they figured out was that if you look to see not the main classification result, but you looked under the hood to see what was coming out of these convolutional layers in the middle, you got these kind of funky, stylized versions of the images that were actually kind of interesting to look at, right? And depending on where you took the output of the network, you could get these things that look like kind of these acid trip fever dreams of like, LSD, kind of like, crazy towers and swirls and stuff like that. And this was all kind of like, generated by just kind of asking the network to, take some sort of random input and spit out something in the middle on the way to getting a classification result. And the results that you could get were really cool. And then the idea was that if you applied this to video, say you were training an algorithm that was supposed to be able to recognize like dogs, right? So here you would get this input video just like walking around the shopping mall, and the output is like this weird, swirly, like there are some trippy textures, and then you occasionally see like dog snouts and dog noses and stuff like that as you kind of push through the video, right? And again, this came like directly out of, just like this image classification algorithm that wasn't ever intended to do anything like this, right? So dogs and fish and all sorts of trippy textures and so on. So this was called Deep Dream, was the algorithm. And again, this was never even published as a paper, I don't think. It was just like someone that they put it on archive or they put it on GitHub as, here's this cool thing that we could find in our algorithm, and people started to use it, right? So this is an example of artists starting to just like use stuff that they found on GitHub to make art, basically. There's also a lot of work on kind of continuing the theme of, take my photograph, make it look like a painting. So, that idea kind of continued in the age of neural networks and deep learning. So you could take your photograph and you could then provide an example of, here's my original photograph. I don't know why I lost my cursor here. Oh, so here's my original photograph, and here are 3 classic, paintings. And then I can say, use this content, but then use this style. And so this idea of decoupling content and style became known as neural style transfer. And so, again, you can imagine that you could take a picture of RPI and make it look like Starry Night, right? Now you can just kind of find a piece of code on GitHub that will do that for you. So let's talk about some of the stuff that's under the hood that enables some of what's kind of currently going on in generative AI. So one thing that we did talk about during the PCA lecture was what's called an autoencoder, right? The idea behind an autoencoder is super simple. You have input and output, and you try to have the input and the output are exactly the same. But what's different is that in the middle is this much lower dimensional latent space. And so in PCA, for example, we talked about how you could take some high dimensional input and crunch it down to some number of principal components. That process is a linear transformation. But if I allow that neural network to have tan H's and ReLUs and nonlinear functions, then it's kind of like doing some sort of a nonlinear PCA. And so an autoencoder is basically like a nonlinear PCA where you represent objects here in the latent space, and then you can expand those objects back into things that look like outputs, right? And so you train this pair of networks, or actually I guess you train this whole network, but then to make new pictures, you just create some point in the latent space and you project it out into the output. And this produces pretty convincing human faces, for example, right? So this was like, a type of autoencoder from 2019 where already you could make human faces that look pretty good. And then for other classes, right? So you could take all the classes from ImageNet, for example, and use them to make like a thing that would make realistic jellyfish or a thing that would make realistic snails or flamingos or whatever. And of course, if you drill down to what these things look like, not all of these pictures really do look like flamingos or jellyfish or snails. The more images you have from the class, the better you could get results, right? So, the dog images are generally not bad, and the human images are great because there are so many images of people, but some of the smaller classes were maybe not very well represented. But this was still like a beginning step in the right direction. The thing that really took off was GANs, Generative Adversarial Networks. And so we'll definitely spend a few lectures in my class next semester talking about GANs. The basic idea here is that you train 2 neural networks. One is very much like the autoencoder part. It's called a generator. So you're basically training an algorithm to make realistic versions of the stuff that you showed it as training data, okay? And then the other thing is a classifier. It's called the discriminator. And so the discriminator takes an image as input and basically outputs a decision. Is this real or is it fake? And so the idea is that you're simultaneously trying to train the generator and the discriminator to do better and better, right? So in the beginning, the generator is making not very good examples, and the discriminator has a really easy time of telling these apart, right? And so then that forces the generator to be cleverer and craftier and making things that it thinks is going to fool the discriminator. But of course, that classifier is also getting better too. And so the idea is you're trying to kind of keep these things going better and better. The better the discriminator gets, the more subtle the generator has to be in trying to make things that really look real. And so by the end of the day, you've got a generator that's able to make really realistic images. And so, again, this was applied to examples of computer vision databases, so you could make very realistic, bedrooms or very realistic cars or very realistic cats, right? And then people started to work on, okay, so this is cool, like I can just kind of sample in the latent space and make a realistic cat. Oh, question, yeah. So the discriminator is basically taking a stack of potential real and fake images and making a decision, 1 if it's a true image and 0 if it's a GAN generated image, right? So the classifier is trying to tell between real and fake, right?
So it's an EM kind of situation if it was flipped.
So is it an EM situation? It's not exactly an EM in the spirit of like kind of seesawing back and forth between the generator and the discriminator. That's true. You're kind of constantly training these things. And I will say that training a GAN is complicated, right? Because like if the generator gets, well, so a little bit hand wavy, basically if they get out of sync, you have a problem, right? Because like if your discriminator never learns the difference, doesn't matter how good the generator is, the discriminator will always get things wrong and it doesn't help get better. So you have to kind of keep these things in lockstep in a way that they kind of continue to evolve well, and it may take several tries as the person who's trained the algorithm to make it work, right? So they are a little bit fiddly, I guess I would say. So here's examples of GAN-generated images. The thing that was incredible was that you could kind of like move your way around the latent space and generate kind of morphs between different points, right? So like if I said, here's one face in latent space, here's one face, and I draw a line between them, interpolating that line will make a face that kind of moves from one to the other. And so all these faces are not real, right? Even though individually they all look pretty great, right? And so it's kind of mesmerizing to see like the skin tone changing and the glasses coming in and out. I mean, one thing that you can see is like the eyes and the nose are kind of in the same place all the time, even if the head pose is changing. So it's a little bit like eerie to watch the eyes staying in one place as the rest of the head kind of swivels around, right? So certainly, like I said, any sort of like, there are lots of cases of like fake LinkedIn profile pictures and so on that could easily be generated by the style GAN technique. And this was only a few years ago. It's only gotten better now. But the interesting thing was people were very interested in how you could then push these GANs around to make more directed images, right? So when I sample a point in the latent space, I just kind of get what I get, right? The question is, can I kind of coax my GAN to make pictures that are more like what I want? So for example, this is a case where I have a source image on the left-hand side and a source image along the top. And the idea is that I can take some from the column A and some from column B to make these kind of composite faces to say, okay, I like the general coloring of this person and the color of the background, but I want them to look more like this, right? So here I can make this similar looking thing. Now it's a person with glasses, and now it's a person with, curvier eyebrows and straighter hair, and now it's a kid, and now it's someone looking to the left, right? So you can kind of see that each of the columns kind of looks like the same type of person with the coloring from these people. And conversely, you could say, okay, actually I want to keep this part more strongly, right? So like for example, this woman here, I want to, keep her face, but I want to take the coloring from the people in the top row, right? So here you can kind of tune, say, okay, I want her cheeks to be a little bit shinier and her skin to be a little bit tanner, right? Or I want her to be blonder. And so the idea was that you could take kind of like the levels of the GAN from different people and combine them together to make these faces that had kind of combinations of the two. And then people were very interested in exploring how you could assign kind of meaningful directions in this latent space. So for example, here it was found that by moving in a certain direction in latent space, the effect was turning the head pose of the human, right? So the kid starts on looking to the right and he starts looking to the left, right? So it's basically the same expression and the same identity, just there's one direction in latent space that corresponds to moving the head. So you write that down. And then you say, okay, well, I found this other direction that corresponds to the kid's hair getting lighter, right? So I write that direction down. And then you could kind of label those knobs and have the user kind of say, okay, now I could take an example and I want to then say here, this one is making the person look older, right? So the endpoint is this 40-something guy, and I turn the age knob up and he suddenly becomes an older guy. And the middle is like saying, okay, now I'm going to turn the white hair knob up, right? Now he looks like an older man. And then this is like the angry knob. So his expression goes from, kind of happy to angry, right? So you're assigning these kind of like, directions that you discover to these knobs. And then an innovation of this that came out of, I believe, IBM and also NVIDIA, I thought that NVIDIA was involved, or maybe it was just IBM, was kind of like, again, this amped up paint by numbers scheme where, again, you could decide on, I found out there are these layers in the neural network that correspond to doors and grass and dome and sky. And then you can kind of just like adaptively change an image by sketching, and in real time it will recomposite the image. Now there are tools that do this much, much faster and much, much better, but at the time, this was still pretty cool to watch. So one thing that also was crazy to see happening in real time was that it used to be that you would submit a paper to a conference and you would wait for 3 or 4 months and then it would get accepted and then it would come out and then people would start to talk about it, right? Now the way it works is that you basically, submit your paper to a conference, you put it in an archive at the same time, people find an archive and they start to use it, and by the time the conference, accepts your paper, tens of thousands of people have already downloaded it off of GitHub and are talking about it and screwing around with it, right? So like this is an example of an algorithm called pix to pix, where the idea was, again, you provide some sort of input and you produce some sort of output. And so here the idea was, for example, take a sketch and turn it into a cat, right? And so edges to cats, or you take a sketch and you turn it into an old-timey portrait, or you take a sketch and you turn it into, kind of an abstract photograph, or you take a sketch and you turn it into Bill Gates, right? And so the idea was that people started to play with this because the code had been made available, and then when the paper actually came out, they cited all these things in the interim between our paper being reviewed and now, here are all these cool things people have done with our work, right? So really things have changed a lot. Like some of the stuff I'm going to show you a little later, again, people were talking about it well before it was ever actually officially published anywhere, which is kind of a crazy thing for me to see as a researcher who grew up in the old school, right? This is just another example of kind of like, again, kind of going back and forth between photographs and pictures. You can kind of say, okay, I want to make sure that the cycle of taking a photograph and turning it into a picture and turning it back into a photograph, or I'm sorry, taking a painting, turning it into a picture, and then turning it back into a painting, that should be kind of like mutually consistent. And so by enforcing that cycle constraint, you could make better results, is what this paper was about. Again, this is more kind of paint by numbers, right? Where you say, okay, I supply a mood on the left that is like a real picture, and I supply a sketch of where I want things to be, and then I can make these photorealistic looking things that correspond to both the mood and the content. So again, trying to separate style and content. And of course, this kind of came into like, there was a while you could play with stuff in, Snapchat and so on, make yourself look like the opposite gender, or make yourself look like an old man, right? So now I want to talk a little bit about how, like I said, it became possible for just average people to download this code and start to play with it. And some people who were playing with it were artists, right? So not just people who were like trained in classical art school, but people who were kind of like techie that didn't necessarily have a great background in technology could still create things that were really cool and impressive without necessarily having to know how it worked under the hood, right? So, for example, Helena Sarin is a famous artist who used GANs to make, like this is kind of like a candy store, right? So there's kind of like, it looks kind of fruity and frothy, this is created with GANs. This is a set of GAN-generated lettuce that kind of also, if you zoom in, kind of looks kind of technological. It's got these kind of cool like sharp edges inside the lettuce called vegan. This was a collaboration between Helena Sarin and another artist where the artist provided all the training data for the GAN, his original artwork, and the GAN created things that were kind of like, again, reminiscent of these kinds of cool technological looking things. These are the things on the right that the GAN produced. So this is kind of like a co-production. One artist I like a lot is named Sofia Crespo, and so she got on the GAN revolution and created all these things that are kind of like really cool, often like botanical or nature themed things, right? So this is kind of like a funky looking parrot or a funky looking flower that almost looks like, those scanner photography where you take something cool, you put it on a scanner and scan it in. And especially I like the work that she does where it looks like something that was like an illustration out of an old, anatomy textbook or botany textbook, but none of these birds ever existed, right? So like it looks like a page out of some mythical book that never existed, right? So that work I think is really cool. This is a artist, Mario Klingemann, who trained again on portraits, basically, and then had this exhibit in a museum where it was kind of morphing between these kind of like uncanny valley, kind of European-looking portraits going back and forth. Again, an early use of GANs trained on actual artwork. This is a great example, Memo Acton. So basically, this is kind of like, again, paint by numbers, where on the left-hand side is a real webcam feed of just like him pushing around objects on a desktop underneath the webcam, like this hover cam over here, right? And then on the right-hand side is kind of a coding that says, okay, this yellow cloth is the sea and this blue paper is the sky, right? And then in real time, you could make these GAN-generated, images that looked pretty evocative, right? This whole video is worth watching because he does this with all sorts of different things. Here you've got this power adapter and you change it into, like different kinds of flame, right? or now it's a boat, right? Just by changing what you mean by the coding of different objects. So again, you have a classifier on this side that's classifying different objects into categories, and on the right side is some sort of like a mapping to objects, right? So this stuff I thought was really cool, and the fact that it's done kind of like in real time is also, I think, very evocative and interesting, right? So this kind of came to a head a few years ago when a team of French artists put this painting into an auction at Christie's auction house, and it sold for like, you know, $1 million, right? So it was a huge like wake up call, like, oh my God, someone paid all this money for this thing. This again is like a GAN generated thing that looks kind of like a classical portrait, and kind of cheekily, you know, they signed it with the GAN training loss as like instead of the artist's signature, they signed it with the loss. And then it was a big controversy because actually it turned out that these artists had taken the GAN that was trained by this other artist, Robbie Barrett, and I think that this guy was actually like only in high school at the time. Like he had just figured out how to train a GAN on all these paintings that he had done, and then these artists, you know, kind of took his GAN and then made $1 million off of it, right? So there's a big question about like, okay, who owns this work? Does anybody own it, right? You know, like this was generated by a computer, but you know, is it who generates the algorithm? Is it who generates the training data? You know, like it's a really fuzzy question. I'll come back to that in a second. But definitely this world is raising questions about, you know, who deserves to be considered the author of a piece of work, who deserves to profit off of it. Another thing that was really democratizing was this thing called GAN Breeder that I don't think exists anymore. I mean, it's still out there in a different form where you could kind of take, you know, again, example images and adaptively remix them to say, okay, I want an image that's like 1/4, you know, dog and 1/4 dandelion and 1/4 whatever, right? And you could kind of make these crazy hybrids that were still somehow photo consistent. I mean, not all of them looked great, like this kind of nightmare dog in the middle, but some of them looked really kind of cool and evocative, right? So again, GANs were like all that anyone was talking about, you know, like 5 years ago. But then what happened? Well, what happened was diffusion models, right? So diffusion models are the new hotness that basically is what is underlying, you know, models like DALL-E and Midjourney and Stable Diffusion. You know, diffusion, Stable Diffusion is what this means, right? And it's a crazy idea, and an idea that I still had a hard time wrapping my head around. So I'm an image processor from way back, right? And so one thing that we want to do in image processing is take a noisy image and make it sharper, right? So we all know that like low pass filtering can remove some noise from an image, for example. And so the idea here was that you train a network by showing it a sharp image, original image, and then you add just a little bit of noise. And then you add just a little bit of noise, a little bit of noise. By the time you take a whole bunch of these little bit of noise steps, you have a totally noisy image, right? And then you train another network that will undo that noise, right? So it starts with this total noise image, and then it makes it a little bit sharper, a little bit sharper. And what happens is that you have this image that like emerges as if out of television static from the noise, right? So literally the steps of this diffusion model are taking a totally random image and then turning it into this picture, right? Which that's how DALL-E 2 worked, and it was just like crazy that that could even happen, right? It seemed like it should be impossible. But once you know a little bit about image denoising, that's actually what's happening. Yeah.
So it's like GANs where it's like going from like, it's going to some state and then trying to like revert back.
Well, it's not like GANs. It's more like saying, okay, I start with this noise image, and what you're seeing here is maybe like 50 or 100 steps, right? Where at every step I'm making the image a little bit sharper and a little bit sharper. And at the end, I have this image of this lake, right? So I'm not going straight from the noise to the lake. I'm going from the noise to a little bit less noise, a little bit less noise. And the idea is that it is kind of conditioned on the prompt that you give it, right? So that's the trick, is like, how does it know that this noise should turn into a lake and not a cat, right? That's where the connection between, well, let me just say also for a second that the other thing that kind of makes all this stuff happen under the hood is what's called a transformer. So this is like, again, what everyone's using now to do all sorts of machine learning and computer vision problems. A transformer is a fancy multi-layer network that, again, it's a little bit hard to explain, but the key idea in the transformer is the concept of attention, right? So here, we're all now used to giving prompts to these generative AI algorithms, right? So for example, the meerkats love watermelons, right? So attention is basically a way of putting a weight on each part of this sentence, and then using those weights to help bias the backward diffusion result, right? So for example, the fact that, there's meerkats and watermelon means I should be making, pictures that look like this, right? And there's also some sort of sense of, history, right? So you've got some sort of idea that there's a causal sequence between these words. And so, again, this is really totally hand-wavy because to explain this takes like a full lecture of work, right? The transformer, again, was something that was invented in Google for, I don't think it was necessarily designed for image generation, but suddenly became the key thing, right? So the attention concept was introduced in a paper called Attention is All You Need, like love is all you need. And then that paper got cited like tens of thousands of times and used as the basis for lots of stuff, right? The other thing that makes all this stuff possible is a tie between images and language, right? So I don't have a slide on it, I don't think, but there is an algorithm called CLIP, which basically is trained using like billions, literally, of pairs of images and text descriptions. And so then these images and text descriptions are both embedded into a latent space so that like the picture of a watermelon and the word watermelon are close together in this world, right? So the idea is that now I can use the prompt that you give the algorithm to understand whether an image of a thing is consistent with that prompt. This CLIP algorithm is really underlying lots and lots of these generative AI because everything is based on a prompt, right? And so early, algorithms kind of had a hard time kind of cementing the image that was generated to the prompt, right? So for example, this says an oil painting of a corgi wearing a party hat. Originally you might get something like this, and then as you kind of include text embedding, you get things that look more like what you want, right? Again, this is very hand-wavy. If you take my class, we'll get into this a little bit more precisely. But it enabled kind of like these word-based navigation of the latent space in a way that was really cool, right? So you say, okay, make me an image of a Victorian house, and now subtract off Victorian and add modern, right? And you could kind of navigate through this world of houses that looked all fairly realistic along the spectrum of Victorian to modern, just by kind of like moving around in this latent space. So when DALL-E 2 came out, it kind of blew people's minds. Again, this is an example of navigating between different points in latent space, so you can kind of have like, smooth transitions between different corners of the space that, sometimes there are kind of like rapid state transitions where I go from like suddenly it's a bowl of fruit, now it's a dog, right? But there is kind of like a consistency of style and content that kind of goes back and forth in a kind of a mesmerizing way. But early versions of these algorithms, I don't know whether you play with them when they came out, they didn't have a very good understanding of a few things, right? So they didn't understand spatial relationships very well. So for example, if you asked for a red cube on top of a blue cube, you make it algorithm results that kind of look like this. Some of them are right and some of them are wrong, right? So it doesn't quite understand that red should be above blue. Or if you said, give me a, corgi with a red hat wearing a green bow tie, you'd get corgis with green hats or red bow ties, right? So it didn't necessarily bind objects to, colors very well. Or in terms of size, right? If you wanted to get a cookie next to a glass of milk, it didn't necessarily understand like how big those things should be in relationship to each other to be realistic, right? And the other thing that was really hilarious was the text that came out of early generative models, right? It was always very funny to see the weird stuff that came out of early generative AI algorithms. Now I think it's gotten better, but in the beginning that was like a giveaway for whether something was AI generated, was whether or not it had goofy, derpy language in it. So again, the fact that there is a tie between image and language means that you can kind of push your generated images in the direction of words, right? So you could say, okay, take this picture and now give him a mohawk hairstyle, right? And so the idea is that you're kind of looking to say, okay, the embedding of this image should be kind of consistent with the words mohawk hairstyle while still containing the main content of this image, right? Take off the makeup or make this cat cuter or make it look like a lion, right? And then you can kind of use this in the same way to make like, make people look like Pixar characters or make them look like Nicolas Cage dogs, I guess, is what this one is in the bottom. And then you can download these apps, again, similar to the Face app, where you can put in your face and it will generate you as Rick and Morty and you as Thanos and you as Shrek and you as Simpsons and all that stuff, right? So again, it's pretty crazy that, you just clone a GitHub repo and you can do this yourself with very little barrier to entry, right? You can also kind of bring it back to the idea of, making paint strokes on canvas. You could say, okay, I want to make a, painting that comes from laying down a fixed number of strokes onto a piece of paper, but guided by a prompt, right? So like, you could say, okay, I want a 1,000-stroke painting of horse eating a cupcake, right? So you kind of get these things that are not photorealistic necessarily, but are also kind of like interestingly abstract. And so this is called clip draw. And actually, I don't know if you remember that in ECSC, I keep on trying to get them to do this. They have that kind of robot that we bring out to events that draws pictures of people and so on, right? So like, that's an idea of like taking a photograph and turning it into a line drawing. That's also something that you could use these algorithms to do. There's an algorithm called Clipasso, like Picasso, that does that. And then, of course, one thing that if you ever play with these algorithms, is what's called in-painting, right? So you say, okay, I like everything about this picture except I want to take this happy dog and make him a sad dog, right? So you take a marker and you scribble out over the dog's face. You say, okay, keep everything the same, but just make this new part inside the red area more consistent with my prompt, right? And so the idea of being able to selectively edit pieces of the image to conform with prompts was something that came about a couple years ago. And then the other thing that was really cool was, obviously there are lots of pictures of cats and fire trucks and stuff like that, but suppose you went on vacation and you got this one sculpture, or your kid made this thing, right? No other images of this thing exist out there, right? But if you take maybe 10 pictures of it and kind of, just train one special symbol in your network that says, okay, I understand that these are all pictures of this thing called S star. Now you can take the whole hierarchy of all the pre-trained stuff and make like app icons of this thing, or Elmo sitting in this pose. Or you could take, your child's toy and make it into a lunchbox or a backpack. Again, these are more examples of this, right? Where you take a few pictures of just like, something that never existed before, and then you can suddenly integrate that into all the stuff where you can prompt. And then you can kind of use that plus the in-painting to say, okay, now I want to take, Steve Jobs holding my kid's, cat sculpture, right? Or holding, or this thing sitting on the girder, right? So again, this idea of embedding something that you only have a few pictures of into this, billion parameter model was something that came about last year. This is along a similar line, right? You take some pictures of your cute dog, and then you can put that cute dog anywhere you want. Then there was this thing called ControlNet, which was, again, super cool, where you could guide the output of the diffusion model by some sort of a low-level input, right? So you take this model and you use a pose estimation algorithm, which is pretty common in computer vision, to get this thing, and then you say, now give me a chef holding a plate in these poses, right? So you're taking the pose from this guy, and then you're making the image out of whole cloth from, just this kind of simple control signal. This is a similar thing, right? Where you kind of learn how to go from a kind of a cell-shaded or a line art thing. This is like the control signal, and then you use that to create photorealistic versions of the lo-fi anime girl or the Starbucks logo. This is a cool one. So like here, maybe hard to tell what the control signal is, but if you squint your eyes, you may be able to see it says, "Watch my YouTube videos." Here, if you look at my screen, this is what I see. Oh, okay. Right? It's the same picture, just different scale, right? So it's maybe hard to see from the classroom, but if you're watching this on the video later on, you can definitely see that it says watch my YouTube videos, right? The YouTube is kind of going across the bottom of this robot, right? So again, there's a black and white control signal that is the words, and then there's this high level detail that is the robot, which is pretty crazy. If any of you follow this group of people online, this is the Corridor crew, right? So I watch these guys every weekend. So these are visual effects artists that do all sorts of crazy stuff. And so they recently did this thing called anime rock, paper, scissors, where they took a lot of footage of themselves in these very stylized anime poses and outfits. And they took 1 million pictures, and they also had examples of their favorite anime, and they turned it into this kind of like, very stylized version. And by combining that with, actual, they cleaned it up and put the green screen people in front of like other Dolly generated backgrounds. And this was like something that was made a lot of waves last year, this anime rock, paper, scissors, where, all of the expressions and poses and stuff like that is coming from their original action on the green screen, but it's kind of translated into anime. And then, that also kind of like raised some issues of like, they didn't actually ask the anime creators, could they train on their anime style, right? And they actually made another sequel to this video where they did it in a more ethical way, where they trained only on anime of people that they had gotten permission to use, right? So there's a sequel to Rock, Paper, Scissors that is kind of trained on more ethically sourced data, but we'll talk about that in a second too. So yeah, this is also kind of a fun video to watch. Again, this is when it first came out, right? This idea. Now you can do this much better. Another thing along this line is Harry Potter Balenciaga. So if you've ever seen this is like a combination of a bunch of things, right? So you take image generation guided by the prompts, right? And so kind of I think the way it works is that you get a prompt that describes the character. Like there's no actual image input of of these characters, but you kind of like describe, okay, give me, knowing what you know about Harry Potter, describe Dumbledore for me, right? Give you some long text prompt. And you say, okay, now describe this thing in this Balenciaga style. And then all the other stuff with the camera zoom in and the slight head motion and the lip syncing is like another thing on top of that. So really, this is all sourced from still images, and then the lip syncing and the camera motion is kind of added on later. This was making, you can find, X by Balenciaga. There's lots of YouTube videos like this that are pretty good. So again, there are big ethical questions here, right? So there's an artist named Greg Rutkowski who discovered pretty early on that if you asked Stable Diffusion, make a picture in the style of Greg Rutkowski, it would make something that looked like his style, right? So he does these kinds of like, dramatic, like mages fighting dragons with fire kind of stuff. And it was clear that Stable Diffusion knew about his style, and people were using it as a prompt to make things that arguably kind of looked like his style, right? Similarly, here's a woman, Holly Mengert, who makes these kind of like Disney princess kind of stylized toon looks. And again, it clearly knows about her style also, right? And even for things that are more like sketches, this artist, Sarah Anderson, also, clearly it knows about what's going on here, even though you wouldn't necessarily put this on your refrigerator, it knows something, right? And so this again is a big kind of ethical / legal issue with modern generative AI is you don't know what it was trained on or how it was trained. But clearly it's trained on some stuff that is copyrighted or owned by somebody, right? And of course, once you've kind of baked those words into the model, it's very difficult to just go in and surgically remove all knowledge of these people. You really have to retrain the entire model, and it's not easy to do. There are still vestiges of those things that are kind of baked into the trained model. And so there are some companies like Adobe and its Firefly suite is making a real effort to say, okay, we never trained our image generation algorithms on anything that wasn't licensed to us, right? But that's not the same, that's not definitely true for, we don't know what OpenAI has trained on. And Stable Diffusion is like the Wild West. So basically, if you've ever used these tools, like OpenAI, you have to pay for it, right? Midjourney, you have to pay for it and interact with it through a Discord channel. Stable Diffusion, you can download from GitHub and then just go to town, right? So there's no guardrails on Stable Diffusion in the same way that there is for a paid service. And consequently, people can just kind of maliciously train on whatever they want, right? And so that's pretty scary, right? That the genie is out of the bottle now. Getty Images, I don't know where the lawsuit stands, but they were suing Stable Diffusion for a while because clearly, this generated image is got a Getty image warped watermark on it, and they're kind of claiming that, you could confuse our brand with the stuff that's coming out of Stable Diffusion. You can't claim that these were not used to train this, right? Now, not every image is going to be perfect, right? So, but the watermark is pretty good, but the image looks like mutant people, right? So, I'm not sure where those lawsuits are right now, but I think that the companies are going to have a hard time defending themselves against the idea that slurping up all of Getty images is fair use for training data, especially if they're trying to make money off of their stuff. Just a few words about other things that have been used in the generative world, right? So in addition to images, I guess I don't have examples of music here. You can certainly generate, generative music, generative graphic design, generative 3D objects, right? So you can start with, instead of a totally noisy image, the 3D version of that is you start with just a bunch of noisy 3D points in random space. And those points slowly coalesce into what you describe, a table or a car or an airplane. Or these are just like 3D models, right? Where again, this is like the 3D version of DALL-E, where you describe something and then what comes out is actually a 3D model, right? So these are all examples of, things that are actually under the hood, 3D models that are rendered and textured. And so this came out a couple of years ago. You could imagine that you describe something and then you get it 3D printed at Shapeways or whatever the equivalent is now, right? The resolution is a little bit lower than a 2D image, but still it's pretty credible. And also you could kind of apply the same kind of like stylization of an image into a 3D object, right? So you could kind of make like a 3D rendered world that it comes from a video sequence, but is in the style of some painting that you specify, for example, right? And again, everything is kind of like very kind of texturally coherent. So as you move around this space, the textures are not like sliding around on the surface of the objects. So this is something that was pretty cool. The thing that underlies this technology is something called a neural rendering field, or a NeRF. NeRF, again, is something that made huge waves in 2022, 2021 for representing 3D data. And in my class, we'll talk about a little bit about NeRFs as well. Again, this is another like NeRF thing for faces, where you can build a 3D object and then prompt it to be like, okay, make him more like a mustache man, or make him like a bronze statue, and then morph between these different descriptions, right? So this is something that came out last year. So evil clown, bald, cowboy hat, and so on. Turn to Batman. Yep, so crazy stuff, right? I mean, stuff that, wouldn't have been conceivable a couple years ago. So there are a lot of like influencers and Instagram people. Like this is someone I follow, Karen X Cheng on Instagram, where this is basically like NeRF stuff using an app called Luma. And so if you have the patience to take the footage in the right way, you can make all these like super cool things that all you need is an app called Luma.ai, and you're using this 3D model of yourself that you've created just from your friend and your camera phone. So she's got some cool stuff on her channel if you want to follow her. Again, you can kind of like make these kind of cool looking things. This is all done like with NeRF and not with digital compositing or anything like that. All right, what else? So like I said, there are definitely intersections between this stuff and art and law, right? So in my class last year we had Aaron Hertzman talk about kind of, can computers create art, which is actually a very interesting and subtle question, right? The role of technology in making art has always been there, right? So for example, photography was viewed as a huge challenge to art when it came out, even though now we kind of think of it just as another type of artwork, right? So, originally there was a whole class of artists who were there to paint people's portraits, right? And when photographs were widely available, that whole class of artists was out of business. And there was a lot of talking in the art world about, has photography destroyed art? It didn't destroy art, of course. Art just kind of changed into some other stuff, right? And so, generative AI, again, is something where I don't think that we would consider anything that we saw today art necessarily, at least the stuff that's coming out of Midjourney and DALL-E and so on. But the question of authorship and agency and so on is something that Aaron can talk to better than I can. And then I also had an expert in law, Pamela Samuelson from Berkeley Law School, who talked about all the legal challenges that are currently happening in generative AI, right? So, there are lots of them. And then again, how do they intersect with previous challenges between kind of like innovation and technology, right? So, for example, when Google scanned all the books in the world so you could look at, excerpts of them on Google Books, they were sued by the book industry, and I believe that Google ultimately won that case, right? So like, there's a question about like how much of the stuff that we're talking about here falls into fair use and how much of it is not cool, right? And then there's also the ethical standpoint. I think we talked about this already earlier in our class about, the amount of energy it takes to train these massive transformer-based neural networks is huge, right? And you're not just training it once, right? So this is basically from, GPT-3 was like 2022, right? So 500 more times, carbon emissions than it takes to fly one person from San Francisco to New York. And we know that it's not just trained once, right? It's trained many times over and over again to get the best performance, right? So GPT-4 and its successors, I'm sure, cost even more energy to train, and companies are not necessarily very forthcoming about how it was trained or how long it took or what they used, right? There are some companies who are a little bit more forthcoming. There's some, publicly released stuff by Google and Microsoft talking about, for example, how they choose where to build their data centers in order to be the most, energy conscious. But even then, it's kind of like, is it really a good energy trade-off to be, spending, billions of tons of carbon emissions for making goofy cat pictures? Does that really benefit the people whose, communities are being like pumped, stuff into the air and so on? I'm not sure that's a great argument to make. So let me talk a little about what we did last year in my class, right? So just like in this class, the first assignment in my next class is go out and get a bunch of examples of something that you want to use as the generative, crux of your first few homework assignments, right? So this group, for example, went out and collected pictures of leaves on campus and then used, I believe these are GANs, to be able to make realistic looking examples of leaves and morphing back and forth between them in this kind of mesmerizing way. So I think this was pretty successful. Another group took pictures of Legos. This is kind of low res, but you can kind of see like Legos kind of like blurping into different shapes and so on, right? We generated our own language models. It's actually impossible to train your own small LLM on a local machine. And so this group trained on anime reviews and then was able to generate things that looked like kind of reasonable anime reviews at the end. Although not every review that was generated by this device was so successful. So you can still probably tell the difference between this and a real anime review. Again, this is kind of like control net type stuff. So the input is a QR code, and the output and the prompt is in the style of the Acropolis or in a railroad track or something like that, which is kind of cool. Again, you can take your portrait and turn it into all sorts of crazy things depending on what kind of like algorithm you use. So here, this is I guess going down the direction of making like ruggedly handsome man, and this is in the direction of making like cyberpunk, like sunglasses wearing guy. And so again, you could also, make yourself wearing whatever you want, or change yourself into a stylized kid version of yourself. This person trained images that they had drawn themselves and made things that were kind of like in the style of themselves. And of course, it's definitely possible to make like anime versions of yourselves. And so we saw one good final project on this. I'll show you one example in just a second. And of course, you could do like the infinite zoom kind of thing. Someone chose to do that, where you kind of like make these photo consistent or kind of like, any single frame looks pretty good, but you're kind of like continually pushing into different, cityscapes and mountain landscapes and so on. This was kind of a cool effect. There were lots of outtakes of me doing different things. I gave the class permission to make whatever they wanted out of me, and so we got some weird results there. And I guess I'll conclude this part of the talk by saying that this is now kind of making it into the mainstream again. So if you go to the MoMA in New York City, there's a massive wall by this artist named Rafik Anadol, who has trained this basically image generation algorithm on all of the artworks that MoMA owns. And so people stand in front of this wall like it's a shrine. It's like, so you can kind of see people that are all standing looking at it. And some of it is like definitely kind of like generative modeling. Some of it is more like this, I think is more like a fluid simulation, is kind of what this looks like to me. And occasionally this thing will flip into a mode that has like, things that may be recognized, like, energy difference, zero crossing rate, convolution weights, right? So kind of like it goes to the tech dashboard that looks like super cool to someone who doesn't really know what it means. All of us who know what it means, understand this is just like some sort of like, visualization of the weights of a neural network, right? But it looks cool to the people that don't know anything about that stuff. And so again, this is being offered in the spring, and if you want to kind of delve down to all the stuff I talked about, let me just also show, while I'm doing this, go to my browser for a second. So let me pull up the, let's see, I have to find where these were. So some of the best projects from last year, I just want to show a couple of them. Without the sound, I think. So yeah, this one I liked a lot. So this was basically like a very nice, like anime-styled, or not anime, like kind of cell-shaded styled shots of campus that I thought were really kind of like pleasant and well done. I kind of like the feeling that this gave. And of course, this was before all of the newer stuff like Sora and so on came out, video generation stuff. This was done, I think, frame by frame, more or less. But I really like the kind of balance between, recognizable places and kind of like cell-shaded abstraction that they were able to achieve. You can make yourself look noble in anime style like this. And of course, there's also some, where's the dancing? There's also some dancing for some reason in this video. So these guys borrowed a green screen and, played around with it. And I think the results were pretty successful, right? So just like in, in this class's final project, basically I would ask you to generate a final project that leverages several concepts from what we learned in class, right? And the other one that I thought was pretty good, again, this was before Sora, which is like a video generation thing, which was basically, you would give it a prompt and then it would generate a small, basically like commercial, that contained, voiceover. You can't hear the voiceover. Basically, it would be doing a AI generated voiceover with like 4 or 5 scenes for each description, right? Of course, the more recognizable the character is, the better the rendition is, right? This guy's face looks a little bit messed up, but The Rock seems to be pretty happy about the orange juice. So yes, there's a whole bunch of these. Let's see. These guys were happy with the pizzas. Let's see, the freshest sheep in the world. I think the other one that I liked was the Burger King commercial with Shaq endorsing 50-pound Whoppers.
The king of all kings standing before his glorious kingdom, the Burger King.
Man, that's just one.
Massive Whopper. Oh, that's a little nightmare fuel there, but another huge burger. So anyway, if you enjoy making goofy videos and stuff, you too can make stuff like this. And again, this is all done on, basically someone's machine. If you're going to take this class, you probably do need to have like a somewhat beefy computer or access to one. But, it's definitely in the realm of possibility for anyone who has like a good gaming machine, basically. Oh, yeah, Gordon Ramsay. Too many burgers.
It's a taste explosion.
This is how it starts,
Never had a burger this good. Bring me another one.
You've all seen the Will Smith eating spaghetti one, right?
I think I might have overdone it.
Not feeling good. So there's actually kind of like a whole narrative, here. So this is the kind of good times that you could have in my class if you want to take it. All right, so yes, see more on my channel. Other questions or comments about anything before I wrap this up? As you can see, I think this is a pretty good, pre-Thanksgiving lecture. Yes?
Do you have a syllabus for the course?
Yes, there's syllabus for the course. If you go to the, so basically the best way to do this is to go to, there's a QR code on the flyers. That QR code points to this GitHub page that basically has a detailed list of what we talk about when. It actually has the videos from last year on there. And so every page, for example, has, a list of readings and links and stuff like that. So the website for the course will probably change a little bit, but this is more or less what you can see. So yes, if you see the things, and actually also I would hope, maybe, if you search for this, you'll find it. Does it know about? Yeah, so it's the first hit when you ask for that. So you'll find it that way. Other questions or comments? Okay.